morning, friends. It gives me immense pleasure to be here again for my favorite course, Aircraft Systems. Today I am in lecture number 29. The topic for this lecture is Limited and Full Authority Digital Engine Control System. So in this we have two types of FADEC system. One is the limited and another is the full authority digital engine control systems. As you know, I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I am in the module number 4. I have reached nearly 50% of module number 4, starting from lecture number 26, 27, 28, and this is the 29th, fourth lecture of this module. Before coming to this module 4, I was there in module 1, module 2, and the module 3. Once I talk about the module 1, this covers the 4 important aircraft systems. They are airframe systems, vehicle system, avionics system, and mission system. In airframe system, it consists of 3 important parts of airframe. The first and foremost, one of the very important part of airframe is aircraft wing. Aircraft wing is used to generate the lift of the aircraft, and 95% of the lift is produced from the wing of the aircraft. Wing consists of the airfoil. It consists of the longeron, stringers, separators, skin. Then in the wing we have the ailerons at the tip, and at the root we have the flaps. Then next important airframe system is fuselage system. In fuselage system, it consists of forward fuselage, mid fuselage, aft fuselage, and the tail fuselage. In fuselage, the purpose of fuselage is to accommodate passenger, cargo, and all other things. Third one is the empennage system. Empennage system consists of horizontal stabilizer, vertical stabilizer, and the tail cone. In horizontal stabilizer, it is used to stabilize longitudinal motion of the aircraft. It also consists the elevator, which is made to make the nose motion up or down. Second one is the vertical stabilizer. This vertical stabilizer makes the yawing moment and lateral and directional moment stability. There is a rudder. This rudder is used to give the motion towards the z axis or the yaw axis. In this, nose will go left or the right, like this. This is yaw left, yaw right, and this is happening by this motion of the rudder. If you move the rudder left or the right, your nose will go left and right. If you make the elevator up, nose will go up. If you make the elevator down, nose will go down. So this is the purpose of your airframe system. Next, very important, another system is the vehicle system. In module 2, we have covered some very important vehicle system. First, we have seen the power systems, power generation system, electrical system, emergency electrical system, power distribution system, AC/DC power system. Then we have seen the environmental control system. In environmental control system, we have seen the pressure control, the density control, and the air conditioning system of the aircraft. Then we have seen the oxygen system of the aircraft, which is used to provide the oxygen as and when aircraft is going above some particular height or altitude, aircraft should have sufficient amount of oxygen so that the air crew, the pilot, which are inside the aircraft, they should not have any problem. Otherwise, if there is shortage of oxygen, passenger will feel very discomfort, and if it is very less, there will be a serious consequences of the shortage of oxygen. Then we have seen the firefighting system, how the firefighting system of the aircraft is working. This also we have seen, and we have seen all the systems. Then we have done the icing and anti-icing system of the aircraft, in which how the de-icing is done and how the anti-icing. Anti-icing means we should prevention of the ice. Ice should not form. It is called anti-icing. Once the ice is formed, and how to remove, this is called the de-icing. And we have seen with our lecture that how anti-icing and de-icing systems are working. In module 3, we have seen very important two vehicle system. One is the hydraulic system, another is the pneumatic system. We know that all the major actuators which are operating the flight control system, which are operating the landing gears, which are operating the doors, and also so many other systems are working with the help of hydraulic system. Brakes, spoilers, elevator, aileron, rudders, slats, slots, all the primary and secondary controls, all are working with the help of the hydraulic system. Next, we have seen the pneumatic system, and the pneumatic system is a standby system. If the hydraulic system is failed, the pneumatic system is coming to play. It gives the redundancy of the system, and it is very useful for any automation of the aircraft. Here, you see here, it is a limited and full authority digital and control system. This digital engine control system also working with the help of hydraulic system and the pneumatic system. It is also part of this. So, I am working on this, and I am going to discuss about limited and full authority digital engine control system, FADEC. And FADEC is one of the latest equipment which is used in the aircraft for the purpose of safe flight, to have a efficient flight, to save the fuel of the aircraft and give the best range, best endurance, and best climbing and diving, and all maneuvering can be done with the help of the FADEC system. So, I am going in detail about this system. So, in this, I am going to discuss about thrust control. In this, we have seen the first one is the thrust control, then evaluation of engine control system, limited authority control system. In this, we have the hydromechanical control system, and next one is the full authority digital engine control system. It is called FADEC. It has got advantages of FADEC and operation of the FADEC. These topics I am going to discuss in my today's lecture. So, in the previous lecture, I have seen that we have done the speed and the thrust control, soft speed control, fuel injector, and description of turboshaft engine. This we have already done. So, what is the thrust control and how we are going to control the thrust of the aircraft? And what is the thrust? If you see, this is the engine, and this is the shaft, this is the inlet, this is the compressor, there will be many stages, and the size of the compressor will slowly going down. Then we have here combustion chamber, I am writing CC, and this is the C. Then we have the turbines. The size of the turbine will be increasing. It is opposite to the compressor. I am just making here. And then here we have either we have the nozzle, or we have here the propeller. So this is and how the thrust is produced? Thrust is produced by either the nozzle or by the propeller. So if it is a turbojet engine, this nozzle is used to produce the thrust, and if it is a turboprop engine, this nozzle is not, this is the cutoff here, and this will, only propeller will suck the air and it will, volume will push the air behind and aircraft will go forward. So this is the purpose of, this is the, how the thrust is produced. But here how the thrust is controlled. So this we have to see that how the thrust is controlled. For thrust control, the control system uses a main control parameter which is directly related to the thrust of the engine. This parameter can be N1 speed. So for the controlling of the thrust, there should be one speed or RPM of the engine, and that RPM, the main parameter RPM, which is related to the thrust, is N1 speed, or the engine pressure ratio EPR. So either you have to take the N1, or the second is engine pressure ratio. How much pressure is generated from one stage to another. Which of the two is used depend upon the philosophy of the engine maker. Like GE, AE and CFM use the N1 speed. Rolls-Royce and the Pratt and Whitney use the EPR. So different manufacturer, like this is used by the P and Pratt and Whitney. This is used by Pratt and Whitney, and this is used by our GE and CFM. N1. N1 is the main parameter for these two engine manufacturer, and the Pratt and Whitney and the Rolls-Royce, they are using the EPR, engine pressure ratio. If the N1 is the main control parameter, the control system keeps the airflow through the engine constant by adapting the N1 speed to be changing density of the ambient air. So if we are taking that N1 is the main control parameter, the control system which is involved in this keeps the airflow through the engine constant by adapting the N1 speed to the changing density of the ambient air. For this purpose, it must receive the information about the air density from the fan inlet. So, for this purpose, it must receive the information about the air density. So, it should get the information of air density from the fan inlet. So, from fan inlet, it should get about the air density of the aircraft, of the atmosphere. Here, what is the N2 and what is the N1? This we have to understand that N1 is the speed of the fan and speed of the LP turbine. And this is the fan. Okay. So, these are the low pressure compressor area and this is the low pressure turbine area. So, this is called the N1 and N2 is high pressure area. It is from high pressure compressor to the high pressure turbine. This red zone, it is a high pressure turbine. This one, amber color, and the red color is your high pressure. I am making this double one tick. This blue color is, I am making here a star like this, and this is a star like this. This is N1, and these tick marks are the N2 zone. So this we have to understand that what is N1 speed and what is the N2 speed. N1 basically relate to the low pressure zone of the system, and N2 is a high pressure zone of the system. So power management control, the inputs necessary for this density correction are the pressure and the temperature from the fan inlet, but this system can only adjust the high pressure rotor speed to the changing air density. So how this power management control is done? The input necessary for this density correction are the pressure and the temperature from the fan inlet. So if you see here, from this fan inlet, pressure and density. Pressure and density we take, and accordingly we have to sense this pressure and density. Pressure and the temperature from the fan inlet, but this system can only adjust the high pressure rotor speed to the changing air density. So this can only adjust the high pressure zone. This unit is an N2 control unit. In this N2 means high pressure control unit, because the N2 is the only shaft speed information for this control unit. And you know that N2 means it is a high pressure zone. This center part, this is the high pressure zone. So in this management, power management, N2 is used, not N1. So this unit is an N2 control unit, because the N2 is the only shaft speed information for this control unit. The matching between the two shaft speeds changes with the deterioration of the engine, and the actual N1 speed will always be a few percentage below or above the correct N1 for a thrust setting. If the control unit controls the N2 only, so if it is, we are only controlling the high pressure zone or the high pressure compressor and high pressure turbine speed, then N1, because N1 may change as per the engine is getting older and older, the N1 RPM may vary some percentage, so this result may not be correct. But N2 will remain most of the time will be same. For the precise control of the thrust, it is necessary to control the fan rotor speed N1 precisely at the correct value for the demand of thrust. But we should make sure that N1 should be the correct. Then only you will get the, because 50% of the thrust you are getting from the fan. So this fan has to be very much precisely calculated, the speed of the fan. Control system with hydromechanical flight control unit use electronic supervisory control unit as an N2 controller additional to the N2 controlling flight control unit to solve this problem. So we should have one N2 control unit also should be there, and N1 control unit also should be there. Both should be there, then only accuracy of the system can be obtained. Such a supervisory control unit, for example, is a power management control of the CFM 80C2. So in this engine, if you see, these systems are used. So in this engine, CF680C PMC version of this power management system is using this N2 control system. So here we can see this flight control unit. What is the flight control unit? I have shown here this diagram. Figure inputs for a flight control unit with thrust control capability for a twin spool engine. Twin spool I have shown. This is the twin spool engine. What is the meaning of twin spool engine? So in the twin spool means there is a two pressure zone. It is a twin spool engine. In this, if you see here, we have the two pressure zones. One is star mark, that is the low pressure compressor and turbine. Then we have high pressure compressor and turbine. Okay, so these are this is called the twin spooling or spooling of the engine. So here if you see, we have here the system in which start lever is here. Here the fuel is coming from here. Metering section is there. Computing section is there. Power management system is there. Then here we have N2 sensors from engine. T20, PS12, N2, PS3, T25, CBP, VBV feedback, VSV feedback, and fuel to the engine it is going, and by these all sensors these type of sensing engine, they are sensing, and accordingly here there is a computing system and here is the power management system. These things will give a metering how much quantity of fuel is required for that particular operation of the engine. So this type of management, fuel management system is achieved in the aircraft. If the control system uses the engine power ratio as the main control parameter, it keeps the thrust constant by holding the EPR constant. So if we are using the EPR, so either we have the N2 or we have the EPR. So I have told you that few aircraft they are using EPR, like our Pratt and Whitney and Rolls-Royce, they use the EPR, and CFM and GE, they use the N2 or N1 system. So this EPR as a main control parameters, it keeps the thrust constant by holding the EPR constant. So it will make always EPR is constant inside the engine. Thus it also keeps the airflow of the engine constant. So by keeping the EPR constant, it makes sure that airflow of the engine is also constant. The N2 controlling FCU is overridden by the EPR controlling electronic supervisory control unit. This EPR control principle is used on version of JT9D7R4 and RB211-524 engines. These are the engines name, and these engines are from CFM, and these engines has to be used under the EPR, and this EPR is overriding the N2 system and it is supervising as a supervisory control system of the aircraft. Now here fixed relation between the thrust lever angle, that is called TLA. So there is a fixed relation, a lever is there. If this you take the lever and you just make it is 0, slowly it will show how much you want. Accordingly, as you shift the thrust lever angle, the demand thrust exists as shown in the figure. This you can see here. I will discuss. For a specific thrust, the pilot always selects the same TLA because the control system can't control the thrust directly. The supervisory control unit calculates the value of the main control parameter N1 or EPR in relation to the demanded thrust. This is done in consideration of the actual atmospheric conditions. The result of this calculation is called the N1 command or EPR command. This we have to understand these words. For this calculation function, the term power management is used. Okay, so what is the meaning of N1 command and what is the N2 command? So we know that the control system cannot control the thrust directly. So there is a supervisory unit or the supervisory control unit that calculates the value of main control parameters, means how much N1 is required or how much engine power ratio is required in relation to the demand of the thrust. Means how much demand is required. With this much of the demand, how much N1, the speed of the your fan is required, and how much engine pressure ratio is required inside the engine, how much compression ratio you are getting. Accordingly, this is done in consideration of the actual atmospheric condition. This will be done by the help of taking the atmospheric condition. This you can see, all this temperature, pressure, this is temperature, this is the pressure, this is the pressure, different pressures it is measuring, and then only it is giving the output. The result of this calculation, so it is calculating, and this result of this calculation is called the N1 command or the EPR command. So whatever the calculation you are getting, how much N1 required or how much engine pressure ratio is required, as per that this will calculate, and for this the function of the power management is used. So in this power management, PMC is used. So this you can see here that here is a thrust lever angle. So here this is the 0 angle, and as you go towards the minus, it is a reverse thrust. And if you go towards the positive, it is a forward thrust. So reverse thrust you have less, but forward thrust you have the more. So it is a maximum for the takeoff. We should use this much 45 degree of the lever. So if this is the lever position here. This is the forward. Okay, here this is the 0. Here is, this is the 45, and here is the minus 45. So this can go up to minus 30, and this will go at a minus 45 degree. You will get the maximum thrust. So like this, you have to move this either this side for the forward motion, and for the rearward you have to make in this. So reverse thrust it will come. So here we have the flight control, fuel control unit. Here we have the fan inlet temperature and the pressure. So it is atmospheric condition. From here either it will T and the P. It will be calculated. This TLA will be fed here. N1 will be here. Speed of your fan speed, fan inlet temperature and the pressure. These are the feedback which is giving to the PMC, and it is a N1 or the EPR command here. This will give speed of the trim signal, and it will go to the flight fuel control unit. And here the quantity of fuel will go more or less. So in this way, it is shown here the relation between the thrust lever angle and the demanded thrust. So how much thrust is required and how much angle is required, this plot shows about that parameter. Here this unit is called the power management control, PMC. The PMC compares the actual N1 to the N1 command. If there is a difference, the PMC override the speed control of the FCU. To do this, it changes the N2 speed until the actual N1 speed equals the N1 command. In an EPR related system, the supervisory control unit operates similarly but compares the actual EPR to the EPR command. These thrust control systems were the last design using hydromechanical control systems. Engine developed later use pure electronic control system. Because of the digital computer is the only control unit and it has full authority over engine control. These systems are called full authority digital engine control system. So till now I have shown a semi automatic control, but after that a new system has been developed, and this system is called full authority digital engine control system, or in the short it is called the FADEC. So evaluation of engine control system, it is shown here that how these things are working. In this first diagram, if you see here, thrust lever angle we are giving, then this goes to the computing section. Here engine sensors are there. Here engine sensors, then engine systems, then it goes to FCU, and here it is a valve. This valve will open less or more, and then fuel will go to the engine as per the fuel monitoring valve. It is called the fuel monitoring valve. It will open, it is like a needle valve. It will open or the close and the system will go. So it is a mechanical or the hydraulic signals. Then next stage it goes to the semi-electronic control system. So if you see here, these basics are same. Only here if you see TLA is there. Here we have the supervisory control unit. Here we have the aircraft sensors. All the sensors, pressure, temperature, RPM, everything is sensed. It given to the supervisory unit. Here is the engine sensors. Then it goes to the FCU. FCU will open more or the less FMV. This valve will open. Engine sensor. This is same. Only this system is new here. In this it is not there. So it is a semi-electronic control unit. And this is here full automatic digital electronic control. So here you see we use the TLA here. We use the aircraft sensors. We use the engine sensors. These all sensors will go to the engine electronic control system. It will go to the engine system. From here it will go. Then it will go the servo valve. This servo valve, I told you the hydraulic systems are here. This hydraulic system will operate and this will open or the close this valve. Accordingly, the fuel quantity will be varied as per requirement. As per requirement, it will vary. So, I think it is very much clear that how this evaluation, this was the first type, old type, then this is the middle, and this is now we have the FADEC system, fully automatic system. We need not to interference, and it is giving a full authority to the engine, and it is not even controlled by the pilot. Everything is done by this FADEC system. Now, if you see the hydromechanical control system, this is somewhat older type of system. So here if you see, here we have the thrust lever angle, we will give some angle. Start lever, you have to push it. Ground idling switching here. Then PMC trim signal. Then it will go to the MEC. MEC, you will get the temperature of the turbine, pressure of the turbine, N2 RPM, PS2 pressure, T25 temperature, CBT, VBV. These all things we are getting. So what is the MEC? It is a main engine control. This is what? Main engine control. PMC is a power management control. CDP or PS3. Then CIT is a compressor inlet temperature. PS3 is a compressor delivery pressure. VBV is a variable bleed valve. VSV is a variable stator vane. PS12 and the T20 from the fan. These are taken from the fan. So these abbreviations which are given, these all are the sensors. These sensors are taken the signals from the respective places. FADEC system, full authority digital electronic control systems, digital engine control system, sorry. So full authority digital engine control system is used for engine control. This has the advantage that is computer can process a lot more parameters than a hydromechanical control system. Therefore, this capability of the system is used for additional functions to optimize the engine operation. Additional to the basic engine control functions of power management and fuel control, the following functions are usually assigned to the system. Monitoring and fault detection for the system and all the connected components. Data source for engine indication. Data source for electronic control management. Starting, shutdown and ignition control. Control of thrust reverser and automated system test. So these are the tasks which are assigned for the FADEC systems. So what are the advantages of the FADEC system? This I am going to discuss about this. So FADEC systems are N1 controls system or EPR control system. Either it controls the N1, the speed of the fan, either it is controlling the pressure ratio, engine pressure ratio of the constant thrust control. They will maintain a constant thrust control. The main advantage of the ability of the system to process more input than hydromechanical system. So what is the advantage? Ability of the system to process more inputs. So in this, more number of inputs can be processed comparing to the olden type of hydromechanical system. The system keeps the dN2 by D2 constant over the whole engine life and regardless of the deterioration. So it will always maintain a rate of N2, change in rate of this RPM will remain the constant. Actuator positioning and the fuel flow control, which is more precisely adapted to the actual engine operating system. So fuel control is very, very accurately measured, calculated, and it is put inside the aircraft so that the aircraft will get the thrust as per the requirement, and the efficiency of the engine is going to increase tremendously. The range and the endurance of the aircraft will be high. Huge data available in computer is also used for performance and engine health monitoring or engine conditioning monitoring. So by the available data of this system, the computer will monitor its health, its any fault going to occur or not. This can be detected in advance in engine conditioning monitoring. So it can monitor the engine. What is the state of the engine? It can be monitored. Higher level of redundancy and compared to the hydromechanical system. This will give the very robust system. The failures will be reduced because in this the more number of standby systems are included. If one system fails, another will start working. So this type of redundancy is very much essential, which is not available in the previous type of hydromechanical systems. A FADEC system is designed to be a fault tolerant, so it will also have less fault. It will try to avoid the fault and reduced workload on the pilot. So also because it is automated system, so a huge amount of pilot stress and the tension of the pilot is reduced. FADEC system design, this you can see here that here we have aircraft here, analog signals, TLA, discrete signals, it is coming to EEC, then power supply, data buses from here to here, starter valve, then we have the reversal system here. From here we have the sensors, we have sensors for monitoring signals, we have the FADEC alternator, power supply. It is inside only. The power supply of the FADEC is separate. It is not connected with electrical power of the engine. That is also one very good thing. Here, fuel to the combustion, it is taken as per the VBV, VSV. These are the bleed valves and other valves. Just now I have explained. And here is the ignition system. Here EEC is electronic engine control and HMU is the height monitoring unit. So this HMU is the height monitoring, and this is depend upon the pressure and temperature of the system. It will work. It is shown here EEC and FADEC alternator. So this you can see here, it is EEC and this is the FADEC alternator. A small unit is separately fixed for this FADEC only, because FADEC, if it is failed, your aircraft is going to be in very big danger. So a separate alternator is used, which is producing the power and which will give always, as and when engine is running, it will give the sufficient amount of the electrical power to the engine and all the necessary emergency supply of the system. Then we have here the circuits of channel A and channel B. Inputs we are giving EEC, channel A standby, inputs EEC channel and all. So what are the sensors in the FADEC? We have P25 and T25 probes for total pressure or static pressure are installed to sense pressure. P25 and T25. These are the probes to sense the pressure. N1 and N2 are the sensors which sense the RPM of the engine. Position sensor, thrust lever and actuator position, LVDT and RVDT are also used. Aircraft engine interface. This figure shows how the aircraft and engines are interfaced. So in my next class, I am going to discuss about the fuel system, characteristics, components and operating modes, fuel tank, safety. These are my references, which is Moyer and the Seabridge, aircraft systems, mechanical, electrical and avionics system. The second book is Design and Development of Aircraft Systems and Introduction, AIAA Education Series. This is also from the Moyer and Seabridge. So any questions you are welcome to ask. I request you people to like and subscribe this channel. I will be coming for the next class after this. Thank you very much for joining. If
like, share and subscribe. Hit the bell icon for more updates.